Faiz, is Faiz here? You Faiz? Yeah. Can I know about your background? What's your background? Where are you from? Like, I mean, from what education line? USM. Oh, you're in USM before. Okay. Oh, so you are junior. Oh, sorry. Oh, you are from Utah. Sorry, I forgot. US. Oh, you are from USM. Then how come you move here? You want to do master here? How do you learn about SMUM? By Munir. Oh, so you want to work under Munir. Oh, I see, I see. Oh, okay. So since you are from USM, you know Johnny or Johnny, how you know about him? Oh, he was your supervisor. Eh? I think I met his student, one of his students before. So who? Huh? Yi Hao? Who? I I think I also met one of his students. I'm not sure where, what occasion already. Suya? Suya? 谁来的？他还在吗？哦，对对对，哦，yeah yeah yeah，哦，that guy，去哪里啊？Go somewhere else, right? Go somewhere else, master. 啊，so he was your supervisor. Actually, I know about him. Yes, because he came to do a master at ANU. I was degree second year. Yeah, there was this time we were studying MA1, equivalent MA1 here. Then no equivalent MA1, equivalent to general topology. Yeah. Then I was very headache. I don't know how to study. And then I always ask him something about assignment. Yeah. And then I think he moved to Adelaide for PhD. Yeah. Oh, why not you continue there? Because no one do tropical geometry. Ah, I see, I see. Oh, okay. Mm, nice. Can I ask what's your race? Arabic, Arabic, Arabic. Are you Malaysian here? Oh, so when's your like your father Malaysian here or no? Are you born here? You born here? Yeah, you born here, but your parents? Also born here. So you guys already come very early. Huh? Okay. Because I thought like you got a bit of Indian feel. Got Indian feel. No. Yemen. Oh, Yemen. Hey, we got a lecturer from Yemen. And then she graduates from USM also. Atlaf. Atlaf. If you know her. Atlaf. Yeah. Also from Yemen. Yeah. She graduated from USM. Okay. Yeah. So let's start. Actually, there's some admin stuff where I want to update you again. So actually, we have total 4 holidays to replace. Last week have on Monday, Tuesday, right? So there were gonna be 2 more Mondays holiday. So this 4 weeks, I think, is very ngam, very suitable for our presentation. Okay, so we'll just move it to presentation. Okay, so exactly 4 of you, right? 4 groups. So we'll do for 2 hours slot. My idea was maybe we can do 4 hour slot at one day. Maybe do a evening time. Maybe Monday, Wednesday, or Friday. Or maybe we'll do it in the study group section since they have a class room. Yeah. Sorry. Hey, how many group we have? 5 or 4 group? 4 group, right? Yeah, we got 4 masters, right? So actually, I got one group done already. So there's one group done already. So I still need finish this from the other three. So I'm not sure you can get the complete set of name lists, but try give me some incomplete if you don't have the complete one to me by the end of today lecture. Okay. So if masters haven't get in touch with undergrads, so please go and ask them. If you are an undergrad, you haven't found your master, go and find them. Find your master. Okay? Go and find your master. Okay? Yeah. So I mean, this is one way to learn to socialize in life. Even in your working place, you need to socialize. How to form groups? There are two ways. One way is you like the vibe of this person and then you go work with him. Or the other one is you have the same goal. So we have the same topic, then we can work together. So different ways to match with people. So if you haven't found one, please find it soon. Don't want to wait until next week. We have to start soon. Okay. Hi, Ivan. How are you? Welcome back. I was like, hey, where the school start? Why Ivan IG still outside? Oh, you know, at that time when I stay, I got sick at China. Ah, you got sick at China? I sick for 4 days. Then I sleep at hotel for days. Okay. You go out and then I didn't go. Oh, okay. You mean you go? Oh, yeah, okay. You say you were sick outside. All right. Okay, I think that's all. I think so. Replacement research group. Okay. Okay. In that case, let's start. Okay. Yesterday someone said that a bit too fast. Try to slow down a bit. But feel free to slow me down every time if you found anything that you don't understand. You miss. Because sometimes, right, it's my problem. For example, I give you an example to yesterday. So, for example, Lydia, right? Lydia says that for this map here, okay. Actually, when I presented yesterday, right, I didn't tell you this line here. Okay, I didn't tell you this line. I just tell you that there's a one-to-one mapping here. And then I write down the map for you. So if you are observant enough, you will actually notice that there's one coordinate disappear in the coordinate. This is something that I didn't say by word. Okay. So maybe it's better if I say by word, I say, oh, removing the anal coordinate and then we get this one-to-one correspondence. Maybe it's like clearer at least. Okay. Other than you need to look at this, understand yourself. Okay, so this is something that you can often point out in this class. Okay, I try to make explicit as possible what we are doing. Because sometimes you need to understand. Sometimes in our culture, right, we didn't write things too explicitly because sometimes we understand. I mean, just write it down, we will like, see it. So we didn't make it super precise, super explicit. But I think it's better we do this so that everyone is not missing what we are doing. Okay, yeah, feel free to point out. Okay, no? So sometimes it's not because I'm too fast or you're too slow. It's just something that you don't know what I'm doing. Okay. 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 So let's do some recap first before we start. So let's do some recap. Ivan, can you catch up, Ivan? You hope, okay, please catch up. Otherwise, I'll be in big trouble later. Where's my lecture tool? Okay, here. Okay, so let's do some recall first before we continue. So basically, yesterday we just introduced two kind of objects. Two kind of objects only. So one is affine space. The other one is projective space. Okay, so The notation for affine n space is both A, then n at the top, and then with some field, or meaning where we pick our numbers from. Projective space, we use both P, okay, power n, and also subscript k, subscript n. Affine n space is really simple. Okay, so if we take, for example, if we take n equals to 2, what is it? So as a set, this is just what? Alpha n space, what? As a set is what? Kn, right? Kn. So it's just n couple of k. So there are n couple of them. And this is not surprising, right? This is what you see in linear algebra if a k is real number. Okay. And if you go complex analysis got do Cn or just C. Just C. Okay. So if it's complex and then n equal to 1, then this is what you see in the complex numbers, and what you do in the complex analysis. So it is n equals to 2, right? And then let's take k equals to r. This is just r2. So yeah, your r2 look like this, something like this. And the points, yeah, all these points you take. Okay. How about projective space? Projective space is a bit different, right? So we define projective space as a set of equivalent class. By equivalent class, so since we talk about equivalent class, right? So what's the equivalence relation? And what's the space we consider? Okay, so what's the space we consider here? A n plus 1, okay? Okay, proportional by some equivalence here. Okay, so one thing you should notice here is we somehow go up one dimension. One dimension. I don't want to use one dimensional because if I talk about dimension, maybe you need to talk about what's linearly dependent basis and something like that. So we just add one more tuples. Okay, just add one more tuples, but we impose a equivalence relation here. So what's the equivalence relation here? Define. Oh, sorry. We need to remove origin, right? We don't want to do about origin. Why? Later you will think about this. So what's the equivalence relation here defined? How does this equivalence relation here define? So meaning what? I mean, before I tell you what this equivalence relation is, right? You should know what are the objects. Okay, we want to equip them together. What are the objects here? What are the objects inside the set? Or what's the element inside the set we consider? What's the element inside the set we consider here? AN. What are the elements inside there? Points. In particular, these are the n plus 1 tuples here. Okay. If these 2 points the same, if and only if, anyone remember? There exists a r not equal to 0 such that ai equals to rbi for all I. Okay. So notice that there are at least two things to notice here. 2 points are the same if every component is differ by the same r. Differ by the same r. Okay, it's the same r. And then this r cannot be 0. Obviously, you can do other equivalence relation. Maybe you can impose different r on different point. But that's not our point. repeat the same arm. Okay, repeat the same arm. Only one arm works. Okay, so that's why this will give us a picture here. What's the picture we'll get, for example, in P1? Yeah, in P1, what's the picture we get? Let's say P1R. Actually, this is RP1. But so what's the picture we get here actually? So what are the points inside the same equivalent class? So meaning you need to ask yourself, when are 2 points that are multiple of each other? When they live on the same line. Okay, passing through the origin, very important. Okay, when they live on the same line, passing through the origin. Okay, so if you stay on the different line, then you are in a different equivalent class. So if you consider all these line, right, you will partition the AN plus 1. In this case, what is our AN plus 1? A2. Okay, we use different. Did you notice that this line partition our space here? Did you notice the partition our space? Okay, so meaning every point in the AN plus 1 only live on one line. Okay, only live on one line. Okay, so yesterday we tried to split this spaces up, right? This space in particular, P1R. Okay, we proved that this space is in one-to-one correspondent. This space is living in one-to-one correspondent. You write it. With A1 K or A1 R in this case, union a point. So let's call it P0. Okay, this is a single. Or how about we just put it as a point? I want to discuss this P0 thing. Okay, union of point. But how do we see this line and a point in this picture? Okay, where do you see line? Where do you see point in this picture? So many lines. Then here just say for one line. How? Where is that line? Where is that line? Maybe it's worth to write it out explicitly now. Yesterday we just mentioned about gradient stuff, but let's write it explicitly. So, well, what are the points in let's call this RP1. Okay, so although we write projective one space, right, real projective one space, sometimes you will see books write RP1 like this. Right, let's call it RP1 in this case. Well, how does this elements inside RP1 looks like? Set of equivalent class. But how do we write down our representative here? I remember. What's a representative? Huh? Sorry? How do you write down? How do you write it down? What's the form? How to write down? Remember yesterday we discussed about punctuation. So how do you write down the point, exact point? Sorry? Puncture line. I want the form. The form of the element. Not that one. Another simpler one. Sorry? Yeah. The comma, A naught, colon, A1. Then we will work with this representative. Okay, so there are two cases, right? We can consider. Okay, we can consider if A naught is 0 or if A naught is non-zero. Two cases here. Okay, let's discuss non-zero first. Okay, if A naught is not zero, right? We said that there's one convenient representative we can take, right? We can consider the representative. Which representative? You still remember? Huh? 1 and A1 divided by A0. Why? Why can we do this? Why can we do this? Sorry? Because A naught is non-zero. So they should live on the same line. I just pick one of them. So in this case, what I do is actually, I just take A0 divided by A0, and then A1 divided by A0. A0 is the R. You know? Okay. Yeah, so we just pick this representative. But what's the implication of picking this as a representative? Where's 1, 0, for example? Where's 1, 0? X, what? X is this, right? So 1, 0 is here. 1, 0. Okay. 1, 1, eh? Where's 1, 1? Oh, here is 1, 0. Where's 1, 1? Which quadrant? First quadrant. Okay, 1, 1 here. And then 1 negative 1, eh? Like this one. So what can you imagine? If you put any real number here, it will occupy the left, right, left or right, right, left. Okay, like this, right hemisphere. Okay, right hemisphere. Okay, so you cover all the points here. Right hemisphere. Does it make sense? Think deeper a bit. What's A1 over A0? Actually, is the gradient of the line. Can you quickly compute it? I use your calculus knowledge. Right, we got a 1, 1 point here. How to find the gradient of this line? It passes through origin, Fair or not? Y1 minus Y2 over M1. It's simply just A1 over A0. Okay. Okay, how about this one? How about this guy? How about this point here? If A0 is A0 is 0, then what's the representative? We just get 0, A1. The okay, but where is this line here? 0, A1. Is the y-axis or the vertical line? Okay, it's the vertical line here. So here is your 0, A1. Okay, but in calculus, what's the gradient of this line? Infinity, fair enough. Y equal to x, y equal to 2x, 3x, 4x, 5x, 6x, 7x, approaching this vertical line, right? Okay, so that's why we define these kind of A0 equals 0 point as a point of infinity here. Okay, and this is why we refer them as a point of infinity. Does it make sense? Okay, so what you see is you have associate your projective and two space here. I mean projective, how many space? One space here, RP1 here, to a semicircle. Hey, does this familiar to you, Sayek? Is this familiar to you? Huh? Is this familiar? Cannot recall. Cannot connect. I thought we did Maslow loops together. RP1. So if we start, okay, this one a bit advanced. I want to talk a bit about algebraic topology here. So if you pick a point in this, you pick a point, yeah. So in this space here, every line is a point. Okay, so if you start from this vertical point here and then you walk along this line, right? And then you will walk back to this point, I mean the vertical line again. This is a loop. So this is a loop in RP1. Okay. Yeah, so you can think that, hey, this loop is not the usual loop that we think about. Usually a whole loop is like an S1. But this one look like half. But actually is a X1 also. Because we identify the top and bottom line. It's the same point. Okay. Yeah. Okay or not? Yeah, if you learn about algebraic topology, you'll know what I'm talking about. But anyway, so can everyone appreciate this one-to-one correspondence here? So we kind of split the projective one space into a line plus a dot. Okay. Maybe I will set out a tutorial question or assignment question to ask you to describe RP2 for me, maybe. Can you imagine RP2 or not? Maybe I thought say a bit less rigorous in class, and then I want you to do in tutorial or assignment, depends. Okay, so let's talk less rigorous here. So RP2, right? Which is P2 subscript R. So yesterday we proved that it is a union of what? A2, A1, and a point. Okay. But where's the picture of RP2? RP2, you need to go to A, which A? A3. Okay, A3, so you need to draw your three-dimensional space. Okay, but we proved that. We proved that what? We proved that this set is actually also one-to-one correspondent to the line that passes through the origin. Okay, so how do you imagine line passes through the origin in let's say R3? How do you imagine? Like your hair, your hair, correct or not? Your head is the origin. Your hair come out like that. Okay, maybe someone is curly hair. Okay, I don't care. But let's say if you are straight hair, okay, so your hair like this, or like a durian. There's a lot of thorn here. Okay, and then where's your A2? Where is your A1? Where is your point? Where is it? Want to think about it? Maybe I let you think about 1 minute. If you can get it already. Maybe I'll tell you what is it, and then I'll lead you to think about how to write it down. How to think about this? Similar like what we did just now, I don't know. But in this case, so what did you notice in the previous case here? Actually, we just pick half of the line. I mean, not half of the line. Actually, we pick all the line. Just that we pick one side of the line. Why is it picking one side is enough? The other side is the same. Similarly here, where is the one side you have to pick? Where's the one side you pick? Chop it. Where you can chop it? I mean, there are a few ways to chop it, but we can chop it here, maybe. Right, chop where is this? Let's label it. So X, Y, Z. Let's chop at the YZ. Okay. Chop at YZ. If you chop it there, anything happen on the left is the same line and in the right. Imagine. Okay. Now from here, starting from here, think about where is A2, A1, and this point here. How many lines you need to consider? Okay. On the right hand side of this plane, right, you have a lot of line. Yeah. You don't forget, on that plane itself also have line. How many of them? This many. No, this is one of the plane, right? You can imagine. This is one of the plane. So that plane already give you this P1, this A1 plus a point. Where to get this plane in? all the rest of the point. I mean, fit all the line here. Can you imagine there's a plan? Can you imagine? Let me draw for you. So, draw here. Wait, just which color better? This color better? Or this one color better? Wait 啊？哪一个 ？Durian color？为了这个 durian 我画少一点。Okay, durian I think I use a darker color. Use this one. Is it better? Use this one. Use this one. Okay, and then we should have a P1 plus a point first. So we got a P1 plus a point. P1 plus a point. And then the rest of the okay, let me draw this circle like this a bit. Okay, how about the rest of the point? How do we include them? How do we include them? So it's like a dome. Is it pronounced as dome? D-O-M-E. It's like a dome. So let's draw it. So can I draw like this? Like this? Is it better? Can you imagine? Okay, a bit chat. Wait. So how should I draw this dome? How should I draw this 3D stuff? Okay, wait. Wait. First, wait. So let me draw this like this. And then here I draw a dotted thing first. And then I draw it coming up. Wait. Like this. Can? Does this picture make sense or not? Doesn't make sense. Wait. How about I draw this one like this? I think this one make more sense. Wait. Okay, let me get rid of this one. We need to know which one is at the back, which one is at the front. Like this. Can. Like. Yeah. Dome. The dome here. Okay. So let me call this. Let's call this dome. Okay. Yeah. I think those who take algebraic topology should like learn this, right? It's homotopy to this guy here. Not sure if you think so. RP1, RP2 is a homotopy equivalent to hemisphere. I think you guys should did this at some point. Okay. Clear? Okay, try and write down the argument. Okay, see if you can write down. Okay, do you have a better idea now? Okay, on splitting these spaces. So one moral is somehow when we study the projective space, right? It's like we study all the affine space together. Okay, for example, is it in RP2, right? There are A2, A1, and a point hiding inside. Right, we are kind of studying the whole affine spaces that's less than equal to n at once. This is very interesting. We not just look at A3, just look at A3, but we look at A3, A2, A1, and point together. Okay. Yeah, there's one way you think about it. Okay, no. Because sometimes in mathematics, we just don't want to just look at one thing. We want to look at things together. And then this is one way to look at peaks together. Okay, yeah. So where did we left yesterday? Let's pick up where we left yesterday. So yesterday we start with a geometry of affine plane, and today we'll continue, and then we'll continue and do a projective plane also. So meaning we are doing the case when n equals to 2. N equals to 2. Okay, so yesterday I asked you to prove that. So the proposition A2 A is an affine plane. But this is not quite true. This is not quite true. We understand this A2 as a tuple. Okay, we want to understand it as a tuple, meaning we don't just look at it as a set of points. Okay, we look at it as a set of points and a set of line. Okay, these two things together define a affine plane. Okay, so where P is a so I don't want to say here equal. Yesterday someone asked me whether this equal is a set equal or what equal, right? So this is not a set equal. Okay, so we just take so instead of just understand the affine two space as a set of point, we need to understand as a tuple. So well, P is a set of point in the affine two space, and L is a set of actually is a set of subset of P, okay, which we call lines. Correct or not? Is this how you think about line? Is this how you think about line? Or your line in your mind is just like straight line, straight line. How you put a bunch of points together. Okay, so it's a subset of P, which we call line. And then we actually define what these lines look like, right? We define what these lines look like in A2 in particular. So these are all the points that satisfy what? So these lines are defined as all the points that satisfy what? So which subset you want to take in particular? Which subset? They need to satisfy a line equation. So what's the line equation here? A x plus by plus c equals to 0. As long as there exists some ABC. Okay, so it's an affine plane. So we don't just simply take some point and then line call it affine plane, right? So it must satisfy some axiom. So there are 3 axioms to satisfy here. Okay, so we need to satisfy 3 conditions. So there are A1, A2, and A3. Okay, so what is A1? Given 2 different points, okay, there must exist a unique line that join the 2. Okay, and A2, if I gave you a line, I gave you a point that's not on that line, then there exists a unique line that pass through the point, but it is parallel to the L, the line you started with. It's also unique, but these two are parallel. Okay, last one. Last one I didn't write in words yesterday, right? So in words, it just says that there exists 3 non-collinear, 3 non-collinear points. Okay, so With the line where we define, you should check these three properties here. Okay, with the line you define, you should check three properties here. Let's briefly go through how we prove this. So let's look at which one easier. Okay, let's start with the first one. Okay, let's do the first one first. Let's talk about the proof idea. I actually put the proof in my notes already. So what's the idea here? Give you 2 points. Okay, so given 2 points. So given, let's say, P equals to x1, y1, Q equals to x2, y2. Okay. You want to show that there's a line pass through it. Meaning what? There's an ax plus by plus c equals 0. When you substitute the xy as these 2 points here. Okay. Okay. Now imagine if ax plus by plus c equals 0, does it imply that phi ax plus phi by plus phi c is 0? Meaning I multiply 5 in the equation. It's the same, right? So meaning if you multiply any non-zero or even 0 also works to the equation, you always still satisfy the equation. That means what? This line equation is unique up to a scalar. Okay, it's unique up to a scalar. Okay, but how to find ABC that works? This is just a question in linear algebra. You set up, so you set up 2 linear system here. Luckily, I taught linear algebra last sem. Then just tell me a ABC that works. Up to a scalar is enough. So meaning what? You can have a one-dimensional, in this case, null space. Fair enough. If you want to solve these, you just want to solve x1, y1, c, x2, y2. Not c, it's just 1, right? You want to solve these homogeneous. Okay, and then argue that it can only have one-dimensional null space. Okay, so this is the goal. This is what I did in my notes. Maybe you can have other geometrical way to solve it, but this is a linear algebra way that I propose. Okay, does it make sense? Okay, I argue in my notes that there's only one-dimensional subspace you can find. The null space is always not one-dimensional, given that S1, S2, and S2, Y2 are different points. Okay, yeah. If you don't want to use linear algebra way, maybe you can use a more geometrical way. I believe there are more geometrical ways. Because why? Because actually these axioms are coming from these Euclidean geometry. Yeah, so they should have a geometrical way. But since I'm an algebraic person, let's use this. Okay. You can find it. You can go and find it. If you found it, maybe you can let me know also. I'm lazy to find, actually. Okay. Okay. So my claim is prove that this system has a one-dimensional null space. Okay. Yeah. Let's don't go to a detail. That's not the main point, but you can check it out in my notes. How about second point? Yeah. So how about this? My point is I split the line into 3 types. So basically there are 3 types of line. What are the 3 types? Can you guess? Is it hard to guess? So basically there are vertical lines, horizontal line, and then the line with a non-zero gradient, right? Okay, so basically I split the line into these 3 cases. And then we discuss on these 3 cases, what line should pass through this point that's not of them. Okay, and then you prove that there's no intersection. So they are parallel. Does it make sense? Does it make sense? Okay, so I mean, well, let's give you what are the three types of line. So, so the first job is to classify the lines into three types, three cases to consider. So one cases is horizontal line. So horizontal line is by the way, this is just my own method. Maybe you can find your method. So x horizontal is y equals to c, and then vertical is x equals to c, and then if m is non-zero, I will call it a slanted line. I create my own terminology. So y equals to ms plus c. There are little words, to deduce this from ax plus by plus c equals 0. You get these three. Convinced or not? Can convince that? Can you convinced by these three cases here? So basically, y equal to c is when a is 0, right? When a is 0. Okay, and then x equal to c is when b equals to 0. Okay, and then the other one is a and b is not 0. Okay, yeah. So discuss for all these cases. So if you have a horizontal line, a point not on that line, how to build another horizontal line. And then is that unique or not? Why doesn't have intersection? So you explain these two things, because you need to show parallel, right? Okay, yeah. Well, I mean, you use your calculus method, how to build another line on the other point. What's the grade? What's the ingredient you need? Gradient, yeah, gradient. Yes, exactly. You give you this, what's the gradient? Give you this, what's the gradient? And then what you need to verify is once you build that line, show that these two lines have no intersection. And then in this proof, you need uniqueness also. Argue why is it unique? If you have other line, it should be the same line. Okay, very standard argument. Okay, I put inside my notes. If you don't understand, you can refer to me. How about the third one? Find three collinear points. Can you find three obvious collinear points or not? I mean, to find three of them, what you need to test, you need to test that there's no single line that contains three of them together. Okay, so let's find three of them first. What are the three obvious points you can pick? 0, 0, 0, 1, and 1, 0. Why is this obvious? Because we are field, right? You should have 1 inside your field. And you should have 0 inside your field. Okay, so this intuition, well, this where do you get this intuition? I mean, you should get it from the R3, right? R2, I mean, in this case. So where is 0, 0, 0, 1, and 1, 0 relative to each other? So 0, 0, 0, 1, 1, 1 here. Okay, and then what do you do? In part A1, what did we show? Every 2 point has a unique line. Okay, so every 2 points should have a unique line. Find that unique line. Ask yourself, is the other one inside there or not? For sure, it's not in there. Check it. Don't believe me, you check it. Okay. Yeah. Is it obvious? Obvious. Should I show you? Should I show you? Should I show you? I mean, I pick a very easy one. I pick this one. This one is y equals to. Is it y equals 0? Yeah. Y equals 0, right? But this point is what? 0, 1. Cannot stay on y equals 0 because y equals 1. Okay. Yeah. Okay. Any questions so far? No? Okay. So for things that I didn't work in detail, please work out yourself. And if not, please look at my solution, see if it makes sense or not. Okay. Any question? No? Okay. So we have seen an examples that A2 is an affine plane. Actually, we can just take it as a axiom. Okay, as long as you have a set of point and a set of line that satisfy these three axioms here, we will call it a affine plane. Okay, anything that you have a point and then you call it line somehow that satisfy this three property here, we'll call it affine plane. Okay, it's not just restricted to affine two space. Okay. 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 So next, we'll do a different definition here. Should we do a different definition? Okay, so let's write down. So in general, let me do a bit more definition before we go into break. Okay, so in general, an affine plane A is a double, okay, P and L, where you call P is a set of points and you call L is a set of sets of points, okay, which we call lines. Okay, satisfying the three axiom, let's not write it down. So satisfying the axiom A1, A2, A3. Okay. Yeah. P. Yeah. Oh, sorry. Yeah. Okay. All right. So next, I think you can easily see that actually parallelism between lines is an equivalence relation. There is an equivalence relation. So meaning what? Again, you have equivalence relation, meaning what? You can partition your set using this relation. Correct or not? Is it correct? If you have R2, if you look at parallel line, do they partition your set? Do they partition? For example, you have this box, right? You have a line like this. Oh, can stick. So if you look at all the parallel lines to this line, do they partition your board or not? Okay, if you have a different line, then different partition of your board. Okay. Okay, second. So this one exercise, very easy exercise. Position. Two distinct lines. They actually intersect, right? So from your intuition, if you two distinct lines, they intersect. But how many points they intersect? What do you think? If you have two distinct lines, one or zero, one or zero. Okay, so you will have at most 1 point in common y. Cannot the line intersect, go out and come back? Cannot, man. Yes, okay, because in this case, we have imposed a very clever axiom here. Actually, it's a 0.1 axiom here. 2 point only have one unit line that passes through. So if you think like what I think, okay, intersect. Okay. So if you think like what I think, so if you go and intersect and then come back again, intersect point, and but A1 says what? If there's a line joining two different points, it has to be the same line. Actually, these two is the same line. Yeah, there's a space like this maybe. Why? Axiom 1, A1. They have to be the same. A1 可以证明的对 A1 是证明的对 That's my point. I just use a different way of argument to let you see it. Yeah. Use A1 to do this. If you have intersect more than 1 point, 2 points, A1 tells you that they have to be the same line. Maybe in some space these two is the same line. Who knows? It's just a form of line, right? Yeah. Okay. Yeah. So you are right. So proof is to use A1. I leave it to you to write it out. A very easy argument. Okay, you say about definition. So let me make 2 more definition and then we can break. Actually 3 more. Okay. So I'll define what a tensor is. A tensor of line. I realize that I think this term is quite important because when I do research in a very deep subject that use tensor, I don't know what tensor means. Although I go tensor, I don't know what's tensor in that. Okay, so what's the tensor of lines here? So a tensor of line is the set of all lines. Again, lines passing through same point. Okay, passing through the same point. Yeah, some point. Okay, it's the same point. Okay, so in this case here, for RP, for example, RP, I mean P1 projective end space, right? Those are also tensor, right? But they are tensor that is passing through the origin. Okay, I mean one-to-one bijection, if you are presenting. So they are bijection with line passing through origin. But in this case here, we move the origin other places. Then we call it tensor. Why call it tensor? 它平衡薄弱有 tensor。不用点那个也可以。Look like tensor， 给我多一点，给我多一点，多一点，多一点。Okay. So if you drop your tensor, tensor 就很乱。So if you have like tensor going through the same point, right? Then you can. Okay, because your tensor too fat already. No, it's not your problem. It's your tensor. Okay, so if you drop your tensor, right? So that like maybe they stick to the same point. The same point. So you can imagine these line as tensor. Okay, so that's why I take it. Next, I will define what is called a tensor of parallel lines. Okay, so these two are different way of thinking. So these tensor don't intersect already. Okay, so they are the set of all lines that are parallel to some line. Okay. So these tensor don't intersect. So depending on what kind of tensor you talk about, tensor of parallel lines, that means these tensor don't intersect or these lines don't intersect. Some line. Okay. Okay, I think let's stop here. Any question before we go into break? Yeah, later we'll continue using this tensor terminology. Okay, let's take a break until 5:08.
Oh, 你这边其实都已经只剩下0和 A1，你干嘛不直接写01呢？
对，我觉得会更好，
如果是
会更好，
写01的话，
可能会更好，
OK，
会更好。A1可能给你以为
以为可以自己
的
选了，
空间
对啊，其实就是01啊。
Okay,
这页我接下来，这页我接下来是干嘛的？哦，批水源不对啊。
哦，这个改了，这个好像水告诉我，康平告诉我了。
OK， 还有这页我觉得你最外面那层加的括号加的干嘛？
最后我加来干嘛？
对啊，你加来干嘛？
我可能一开始没有写这个，
那也不应该再加一层。
我再想一下。
还有这个地方你也多加了一层。
哪一个
？U0应该是这个东西，怎么可能是 U0 这整一个 set 对应到一个点呢？
想一下，想一下。哦，这个才要出现在这里，
不是是
这一个
对这个要
这
出现在这里，然后这边应该是一个
对对，
点。
因为后来我把这个加东西过后，我就把之前的东西乱掉了。
OK
OK，我改一下这个。
我的菜已经改了，你可以去读一下我
OK
看
OK
的
OK 可以。有个问题。
就跟目前学到的东西已经超过目前学到的东西了。就之前你讲，就之前那个 topology 讲过那 open 跟 close 的。
OK，yeah sure，
你看
，yeah sure。
你看，就这个，
啊哈。
它这个 hemisphere 嘛，
，yeah sure。
它这个 hemisphere 它不是一个 open 的东西，或者它这边 RP2 它的那个 hemisphere 跟我们那个平常的不一样。因为你看啊，它这个 hemisphere 它是打到它是可以跟那个 A2 一对应的。
yeah sure，yeah
这样
sure。
子的话岂不是它一个 它这一个 open 的东西打到一个又 open 又 close 的东西？
Well, I mean，
这样子的话，
喂，不，你现在要 understand 这个东西还是在 R3 里面是吗？可能它的 topology 会不会变？
对啊，我觉得
它应该不是在用 ambient topology 了吧？我觉得
不懂。
不是，I mean，平时我们画这个 NC 的时候，其实是在没有 coordinate 的情况下把它画出来，只是在这个情况上来就比较 convenient 啊。But 如果你是讲用 homotopy 的 idea 的话，它其实是没有 coordinate 的。也
对，这样子的话，在那个情况下，
画在这边也没有问题，只是说你不是在用 ambient topology，应该是这样解释。
什么 topology？
因为他这样子画的话，他的 confusion 是这东西又 open 又 close。
哦，
它 open 还没有 close 啊，还没有包括那个边啊。
sorry，不是 open 不 close，I mean 就
对啊
它
，A2 啊，A2
它
是 open
不
close 的东西啊。
喂，等一下，我想一下你要讲什么？因为你要讲，等一下给我想一下。OK，它又不 open 又不 close，你要讲的是，我这样子画是不是又不 open 又不 close？
没有啊，就是两个
嗯
hemisphere 啊，就看到 hemisphere 的右侧啊，看那个 y 在 plane， 看那 y 在 plane 那边的东西。
对啊，
看那个右边的。
对。
啊，这样的话是跟 A2 一对应。
啊，对，没有错。
这样子的话，就你这个 LR3 coordinate 来看的话，它是一个 open 的东西。但你去打到一个 open，
你讲的是 topology R3 topology。
是咯，我就讲不应该要讨论 R3 topology 吧，应该不应该讨论那个，不应该讨论它的呀，应该不应该用 ambient 的？
应该是这样子。
不是，I mean， right，I mean
怪怪的，看起来
也没有什么，不应该讨论什么。
对，I mean topology 很长，就不是用 ambient 的 topology 来讨论的，通常都是我们重新就是重新 define 过。
我没有 get 到你们在 discuss 是什么。
把它变成
就是
之后，
就是这个 you open you close， 但是放在这边的时候就 open 吧。OK，
所以就
有可以练 topology 哦。
对啊，他用 Euclidean topology restricted subspace topology 来这样讲的话，你用的是 subspace topology，但是应该不可以用 subspace topology 来看。
有 metric
它本身是个 topological space 啊，它本身是个东西。
就
对，应该比较正确的讲法就是不要用 subspace topology， 应该是不可以用 subspace。很长 subspace topology 其实是没有什么用的。
可能也不是不可以，是看那个 topology 有什么意思。
像他这个也很厉害哦，你看他那个 y 这边他那个东西，他那个东西是 close， 看起来一个是 close， 他跟这个他跟一个 close 是这应该是 close 吧？
因为 YZ plane 我也只是就一半吧，其实你看。
对啊 ，YZ plane 就他那个看上去它是跟一个 close 的东西，
因为它是一种，
就一个线跟一个点，应该是 close。
你讲线跟点加起来就 close 了啊？你这个意思？
算 close， 应该算 close。但它的那个叫什么
close in what？
但它的 complement 确实 open 就 close 了。
对，不是，你还是用 subspace 来想的啊。我想一下，一个 line 跟一个点一定要 close。
它可以跟那个就一对一这样子，这样子。
帮你写一下，你写一下给我认真想一下，给我认真想一下。我觉得你的问题有问题，然后我现在 point 不出那问题在哪里。你写一下，你写一下，
那个一丁生也应该不是 top 啊，
你写一下，你写一下
只，是在
应该不是 top 啊。
一对里面，
我也想
可以把那个 open 打到 open。
把那个 open，不然你把它打进那个 student forum 里面，你把它打
不是你想到的是，如果有一堆你可以 transfer topology 的问题，你想
对啊，
想到那个，
它是可以的。
所以你是用那个一堆可以 define 一个，哇，一边有 topology 你可以 transfer 的 topology 过来，你讲到那个，
那不是产生
你讲到那个吧，如果你讲他们原本都有 topology 的话就不一样，就没有什么意思。不是讲你各自有 topology 的时候，你可以开始一堆。
我觉得你想清楚，把它写出来，把它写出来，写清楚来，
啊，
写清楚来。我们可以想一下，他们也可以帮你想，我也要想一下。你把它写清楚一下。
我想问关于那 proof 那个 axiom 啊，为什么要去 proof 它？就是
哪个？
三个 axiom
没有啦，就 I mean 一个
它这个
affine plane satisfy 的
F1 space 的
if satisfy 的 axiom。
因为我看你写它就是 affine plane 的 definition，然后你叫我们去 proof 它。
因为我现在是在找一个 object A2K，我要 prove 它是一个 affine plane。我没有教这个东西 affine plane。
啊，没有，我讲
哦，就算教它这个 affine plane，我要它 satisfy 的 property，我也要 check 一下。我只是要 check 一下这东西会符合这个这些条件了。
因为你昨天是写了这三个，然后我听到你叫我们去 proof。
对，没有错，对，我现在就
我本来也是，
对啊，
我本来也是
proof 啊
confuse 这个东西。
就是在 proof 啊，是在 proof，
啊，
或者这样子讲啊，为什么我们叫它 affine plane？因为它符合这三个条件，就这样。
没有，应该是这样，这个 proposition 可能不要出现这两个字比较好
哪一个字？哪一个字？affine plane。
先写那三个 proposition，然后
啊，
过后
哦，
那个用拿来做 motivating example。
Well, I mean,
因为
就是这个
at this point 我们没有 define 过这个东西。
啊，
对啊，我们没有 define 过这个。
所以可能这样写可能会乱在这边，我也是有一点乱那个时候。
喂，
我是想一下才就是呀，你at this point 应该是讲，我们只是拿 A2 做 motivating example， 讲它 satisfy 这三个 property， 然后我们要这三个，我们就是要这三个 property 来 define affine plane。
啊，
我的理解是这样的，不，你的意思是这样的。
我的意思是说，它是这个东西，然后这个东西是符合这些条件。
啊，
就是
他是在说这个东西符合这三个条件，但是 affine plane 是定义在这三个条件。
对
AK2 是 affine plane 呢？
的 confusion part 是因为这两个字
因为
还没有
这个东西
出现
没有出现过，但是就是
对
这个东西，
所以他前面的那一段是只是为了证明 A2 是一个 affine plane 而已。
不然的话就是先 define affine plane 再讲这个也。
对，我知道你这个，我知道你讲的东西。现在我的意思是说，来，这个我的意思是说，这个是一个新东西，然后讲知道是个新东西，因为它符合这些条件。
就好比他先跟你讲 open set 符合这些条件，再跟你说符合这些条件的东西叫 open set。OK，
啊，OK，
一模一样，
没什么问题，没问题。
然后
不然你也是可以把这个移开，就是
我知道你讲，我知道你讲，我知道你讲，我知道你
下面还在写了。
我知道你讲，我知道你讲。
A2 我的 proof 很简单吧，没有分 case 啊，就很快吧。
可以啊，你可以试下写一份升上来，
啊
你可以写一下升给我，你可以写一下升。
哎，你建议我们做什么？
开始题目。慢点再说。
OK。
Let's start. Okay. I think there's some very interesting question from who? I'm not here yet. Okay, later when he come back first. Okay. So let's introduce some terminology. Okay. So let A be an affine plane. Then for each line L in A. Okay, maybe it's not good to write this element. Just say in A. We will denote the tensor of lines that are parallel to L by this square bracket L. Okay, because just now we said that parallelism is an equivalent relation. Okay, so we can pick equivalence classes. I mean, representative for equivalent classes. And at the same time, we will call these tensor as a point of infinity again. Okay, point of infinity. So maybe you can kind of guess what we are trying to do. Sorry? Yeah, sure. That's one of the things we can do. So, but anyway, this point of infinity, what you should think about it now is just a representative. Okay, just a representative. Okay. Right. By the way, just now, please don't confuse by this sentence here. We show that it's an affine plane because we didn't define affine plane at the first place, right? So what it means is I want you to show that this A2K has these two set of things and then satisfy this bunch of property here. Okay, so basically I'm using the statement itself to define this affine plane. Okay. Okay. Let's continue. Next, we'll define the completion. Okay, the completion of A. Okay, so if you take general topology before, maybe this will make sense to you. If you haven't take general topology before, you're gonna take it soon. This is a construction that you're gonna see in general topology when we do compactification. So the completion of A, we call it A bar, is again a tuple. It's again a tuple. So let's put a bar on P and L now. Okay. And then where? So I need to tell you what are them, right? So let's write down what are them. So P is a set of, again, it's a set of points. Okay, let's do like this. It's a set of points. Still points in A, yeah? Okay, but we have extra stuff now. We have extra stuff. So this extra stuff is exactly the points of infinity. Points of infinity of A. Okay, so we just take the representative of different tensor of parallel lines. Parallel lines of different parallel, like tensor of different parallel lines, yeah. Okay. Tensor of different parallel lines. Can I say like that? Yeah. Or different tensor of parallel lines. Tensor of different parallel lines. Parallel lines are different. Huh? Different tensor better. Tensor of different parallel line. And parallel line can be different. I think different tensor of parallel line makes more sense. If tensor of different parallel, what does that mean? Different parallel lines. Two parallel lines are different. Very funny. I think different tensor of parallel lines. Okay. So this will correspond to you take different lines and then you look at the parallel lines to that point, to that line. Make sense? Okay. And then what is L bar here? So L bar is quite interesting. So L bar, there are two things. So this is actually is a set. Again, obviously it's still a line, it's still a line, but we can call it a projective line. Okay, so there are two types of line you can consider, which are either A, the union, okay, union of the usual line and its representative. Okay. So with the point of view infinity. Okay, so how do you imagine this line here? So usually you just take a line, right? Okay, if you imagine RP1, okay. But in this case here, you take that line and the representative of the tensor of parallel lines to that line. Okay. Does it make sense? Okay, so you add one more thing to your line. We call it point of infinity. Maybe now it doesn't make sense why we call it point of infinity, but later you will see why. The other line is what we call the line at infinity. Okay, wow, infinity still got line. How to think about it? Infinity still got line. So let's denote it as L infinity here. So what is this? This is a very artificial line. So we wanted to consist all the point of infinity. So meaning that this line contains all the points of infinity. So what is it? You just simply take the union of all the. Okay, so two types of line here. Okay, so is it clear that we are building on the A? We know this A bar here. Okay, in A we got points, we got line, right? Okay, but in A bar here, our points becomes some sort of. We still take points, okay, original points, but we add in points of infinity. So these are the representative, okay, or the tensor of parallel lines. Yeah.
Why you put point of infinity at set L? It is already in set P, right?
Let me see. What do you mean? No,
I mean, you
No.
already treat point at infinity as a point in set P. Why you
where
also put it in L? Because L is the set of line, right?
What do you mean? What do you mean by already put point of infinity in the?
I mean, you treat point at infinity as a point, so it is in P.
No, I didn't treat it as a point. Where did I treat it as a point?
Because you already write that P contains point of infinity.
P contains P bar. I mean P or P
Yeah,
bar?
P bar, P bar.
P bar, and then
Why you also put it in L bar?
why do I put it in the L bar? You mean this line here? Yeah, sure. I mean, well, I mean just now line says what? It's just a set of points, right? Okay, so I just add one more point here. What's wrong? Yeah.
The thinking P bar and the thinking part B seem to be.
What do you mean? No. The point is saying that this is the point, right? Yeah, sure. I can add the point into my set of lines. Because line, what's line? It's just a subset of points. So basically I just add one more point into it.
Yes.
Okay. Yeah. I just simply add one more point to the original line. Okay. Because this is a middle point already, so I can add the point. It's still a subset of points. Okay. Maybe it doesn't make much sense now. Later you will see. We'll prove it. I mean, that you see something interesting inside the book. Okay? Can you understand? Understand? All these definitions. So we have a new set of point and new set of lines now on top of A. So this is called completion of A. Okay? For question? Can remember or not? I think you need to at least remember, otherwise later you will get lost. Okay, so basically the idea was okay, let's draw it. Let's draw it. So I think one ability you need to get even if you don't become mathematician in future, you need to learn from this math degree is turn a paragraph of words into some image, and then you can imagine. Okay. So for example, we got A here, we got A bar here. Okay. So what is A? A is just a point, set of points, and then set of line. That's it. Okay. So inside this point here, let's call it P, and then inside this line here, call it L, something like that. Okay, a bunch of p at the time. Satisfying, well, satisfying the three axiom, right? So satisfying, is it satisfying three axiom? Yeah, we pick from completion of the affine. I think yes. Okay, so satisfying the three axiom, A1, A2, A3. Okay, and then what is A bar here? So this is a new set of points. I need to tell you new set of points and new set of lines. Oh. Okay, so what are the points we consider here? The old point, we still considered it. Old point, we still considered it. But the new point that we added in is what? Representative for the tensor of parallel lines. Okay, so we consider the representative from the tensor of parallel line. Okay, so what is this? So I give you a line. Okay, look at all the parallel lines together and then pick one representative. Right, just pick L itself is fine. How about lines? Two kinds of lines, right? Okay, one kind of line is the original line union with the representative, okay, of that parallel line. Okay, so what can you imagine here? What can you imagine here? We know that two parallel lines won't intersect, right? Okay, so potentially, let's draw something like this. You got L1, L1 that is parallel to L2, right? But in this case here, they will attach with the same representative. Okay, but L1 shouldn't equal to L2. Okay, but they're attached to the same representative. Okay, no? Because they are parallel. Does that make sense? But these two still different line, no? Why? Because L1 should be not equal to L2. If they don't intersect, if they intersect, it is just the same line. Okay. Does it make sense? Okay. So in this case here, yeah. So what I want to say here, maybe let's write down what I say. So this true line is different if L1 intersect L2 is empty, even though L1 is parallel to L2. Okay, so let's make this bracket bigger. Okay, and then the second line is what we call a line of infinity. Line of infinity just contains all the point of infinity, all the representative. Okay, does it make sense? Okay, so can you see the difference between this A and A bar? And A bar. Okay. All right. So let's prove something interesting now. Hopefully we can finish up these by today. Okay. Before that, let's introduce some terminology from the geometers. We'll say that two mathematical objects meet if they intersect non-trivially. Okay? Intersect non-trivially, we said that meet. Actually, why I didn't specify what the mathematical object is, actually, this is also the same terminology we use in general topology later. When two open set meet, okay, they also intersect non-trivially. Correct? Correct or not? 对吗? Is this how you use the meeting word? When you meet with someone, should you meet non-trivially? Non-trivially just means that the intersection is not empty. Yeah. The trivial here is the intersection. Correct or not? Okay. Right. You cannot say you are parallel, but you meet each other. Right. Yeah. All right. So the theorem is, let's prove this theorem. Again, I use the same way of expressing. So the completion A bar of an affine plane A is a projective plane. Okay, I think let me do a better job here. I will underline it. Actually, I want to define it. So it's a projective line satisfying four properties. So satisfying four properties here. So P1, P2, P3, and P4. Okay, what's P1 here? Similar. Okay, it's very similar to A1. So two distinct points. PQ in A lies on one and only one line. Second, similar to what we have proven before, any two lines meet in at least one point. P3 is the same as A3, so there exists three non-collinear points. And then the last one, very interesting. Every line must contain at least 3 points. Okay, at least 3 points. So you can see that most of these are similar to the affine plane property, but we have more axiom to satisfy here. Do you want to think about it and discuss among yourself first? Try and think about it. I give you about 3 minutes. Try and discuss or think about it, how to show it based on what you had. Yeah, by the way, if you have any extra question, right, like given by Heng just now, feel free to post on the forum, okay? Because I think there's a lot of expert here, maybe more expert than me sometimes. So you can get help from them. They can help you to figure out your confusion. Otherwise, I also can help you to think about it. Okay, so feel free if you have, for example, just now Heng asked about topology of RP2, right? Okay, you can put it there. Okay. Yeah, feel free. Okay, not just asking me. I'm not God. I'm not God. I cannot know everything. Okay, but what I can do is I can initiate discussion with you, or I can go and search for you, something like that. Okay, yeah. Feel free to post in the forum. Yeah, maybe others can help here. Okay, try discuss with your friend beside you, behind you, in front you. Hey.
One is just now using the pencil of parallel lines, and the other is using the projective end space where it is x0 colon x colon y. So,
but in this case here, wait, back up a bit. So yeah, sure, I think they should be the same. but not that in this case here, we didn't use the coordinate way to describe it because these are abstract affine plane. So we simply just talk about line. So where this line come from? Just line only. Yeah. So it depends on where we discuss. No? For example, if you want to talk about that case, right? Later, maybe I do a bit of trailer. So what I'm aiming to show you is I'll show you that projective n space is a completion of affine n space, and then from this from this proposition it tells you that it's a projective plane. And then from this correspondence, you should see that the point of infinity that we defined before correspond to this pencil thingy. Does it make sense? Does it make sense? Yeah. So we haven't quite relate projective n space to projective plane yet. Okay, so what we're gonna do here is we prove the completion of an affine plane is projective plane, and then we already know that affine n space is a affine plane. So what we need to left to show is projective n space is a completion. Then we can use this theorem says that it is a projective plane, and then you can go through this go through this language and then see that the point of infinity that we define at first is the representative of some tensor of parallel lines. Yeah. Okay, does it make sense? Can get the logic. Can get logic. Yeah. Okay. So do this first. Do this first. Do this first. Later I'll let you see the big picture. Okay. So I think time's up. Let's do together. Okay. How about let's discuss. If we can do it verbally, then do it verbally. Don't need to write down. So there are 2 points, right? In A bar. How many kind of points you had? In A bar, there are different points already, right? It's not just point in A, it's also the tensor. So, well, if it is just 2 points in A, then you can use the affine plane properties. A1 tells you that there's a unit line joining them. Okay, so this is obvious. It is 2 point of infinity. What line you can use? Line at infinity. Okay. What about if one of the point is the ordinary point, the other one is point of infinity? What's the line? What's that line? Huh?
I think A2 can help us here.
So how does A2 help?
Line here and you point here, you want to find a line that parallel to this.
Wait, you speak like a kindergarten. Okay, let's start very concretely. You talk like this, the expert don't know what you are talking about, you know. So let's write it down. So that's why we would like students to learn proof. You want to set up the things properly. You line, you point, line, point, line, point. I don't know where you take your line, take your point from. Right or not? So you need to start properly. Okay, let P and Q in A bar. So there are 3 cases, right? We already settled 2 cases, right? So let's write it down. So if P and Q both in A, we just use A1 to solve it. I leave it to you to write down all the details. Okay, I don't want to write word by word. You are not second year, first year. Okay, so try and write the whole argument yourself. But in my note, I will write the whole argument. Okay, so you can refer. Okay. Second, if P and Q are points of infinity, we use the line at infinity. Okay, so now the problem is if P is a point in A and Q is some point of infinity. Okay, so what do you do? Right? Eric, you can continue from here. I already help you set out the line and point already.
I think that you can just choose a line L with
Choose a line.
in the pencil of Q.
Is the pencil, yeah, in the pencil to pencil, there are parallel pencil of parallel lines to L. Correct. Okay, so choose M. Do we use the same notation? Let's see. Yeah, we actually use the same notation. We use the same notation. Yeah, we use the same notation for equivalent class and set. Is this unfortunate or not? If I write like this, if everyone happy or not? Or you want to protest?
I think I can understand what you.
I mean, understand is one problem. One thing is we don't want to confuse people. What do you think? What do you think? Maybe we can set a notation here. Tensor is a set of parallel lines to some line. But I think we use equivalent class as the same notation. So how? There's a notational crisis here. Tensor is an equivalent class, yes. But the point is our representative and equivalent class is the same notation. Bracket Q. Bracket? No, the Q is not the problem, right? The problem is this thing. So if we pick this as our representative, can I just put a set?
No, I think L is a representative.
I mean, sometimes we'll write representative as bar or put a square bracket like that, right? I don't know. How about
I don't think the set is a good idea because the set is only contain for one element.
wait, let me think. So wait. So in the discrete math, right? So for example, Z12, 0 bar actually means a lot, right?
Yeah,
0 bar is a set, right? So what's wrong here?
I don't think there's something wrong here.
There's not something wrong here. Nothing wrong.
Yeah,
You sure?
I think so.
You sure?
I'm not sure, but I think so.
I think not wrong. Why? Okay, why I confused last time? I think not wrong. Because this guy also in here. Oh, I think not wrong, not wrong. I think not wrong.
Because equivalence class is
Yeah.
already a set, right?
Okay, sure. But my confusion, I think, is between the set and the representative. I think representative is just changing the L inside here. And then, okay, so everyone can get these differences. Okay, so I just leave it like this. So I'll pick an M in L, and
Then M is passing through P, then we are done.
okay,
If it is not passing through P, then we can use A to see that there exists a line that passing through P and is parallel to M.
well, I mean, so why you are so troublesome one? I mean, if you have an L, right, you should see whether this P is in L or not in L, correct or not? This is the two possible case, right? Okay, so if okay, so let's do it. Okay, so there are two cases here. Then either P in L or P is not in L. Okay. So suppose P in L, what happened? We are done. Why?
Because L passing through P and the L is passing. The L union pencil L is containing pencil L.
Okay, so we are done by picking the line to be L union this representative. Okay, sure, this is the line that connect these 2 points, right? But why is it unique? Why is it unique? So maybe sometimes the textbook will put here why unique. Hmm. And what thing you are using? What theorem or what axiom or what you're using? Why unique? Why unique? Maybe we put here first. We do the second case. You want to answer? Why? How do you prove it? How? A2 start with one line and a point not in there. But now your point is on that line. You want to try or you let me try? I try. Okay, I try. Okay, I leave it here first. Let's do the second case and then I come back. Okay or not? Let's do the second case first. Okay, so the book will say why you need you go and start here first. You start here first. So second, let P not in L. Then this one is easier, like what you say. Okay, because you got the L and then you got a point not in there. Then this is the picture that is A2 give you to you. So by A2, there exists a unique line M such that what? What's the full sentence? This M will contain P, and then moreover, this M will be parallel to L. Okay, so parallel to L mean what? Means what? This M should be live in the tensor that's parallel to L. Then what's this line here? Then the uniqueness is given by A2. So you just take M union the tensor is the required line. Okay. Does it make sense for this part? Okay. So for the previous part, let's do some trick. Since P is in L, right? Because L is an equivalent class. Let's click some other line that don't contain this P. Okay. And then it tells you that that unit line should be L. Okay. If it's not, if it's different, and then there's an intersection, and then the intersection will tell you that something, that two lines should be the same. Something. Okay. Understand what I said? So you can instead. So let me write down what I said. So let's put here Y unique. So we can so instead look in at L directly. We can Can we find? Can we find? We can find. Can we find or not? Can we find? Let's write down first. Can we find M in L such that M is not in P. So M in L such that P is not in M, like that. And then from here you argue that L is the thing you want. If you cannot find, right, then L is the unique one. Correct or not? If you cannot find such M, then L is the unique one. If you can find such M, then I think we can use A to argue that L is the unique one. Does it make sense? Because L is the one that contain already. So, but A2 say there's a unique one. So that one should be the unique one. Does it make sense? Can follow? A question? Question? Okay. Try write these down in full. I think I'll write it down in full also. My lecture note. Okay. Let's see. There are more there are more axiom. Let's do one very interesting one. How about let's do P4. Yeah, let's do P4. I think P2 and P3 quite similar. Let's do P4. Every line contains at least 3 points. Okay. So what kind of line you need to consider here? There are two types of line, right? So one line is a usual line plus a point of infinity. And then the other line is line at infinity. Okay, so there are two lines here. Two types of lines. So how to prove this? What do you think? Yes? Try? Yeah. Okay, so what's the first case? Okay, so what are the 3 points inside L infinity? What? No idea? Well, I mean, you need to realize on the previous point, right? You realize on the 3 previous point here. So I think you are right. The line of infinity one is easier to solve. How about P3? What does P3 give you? 3 collinear points. So meaning what? Every 2 points you have a unique line, right? Then these 3 lines should be different. These 3 lines should give you different point of infinity. I don't know. But your line of infinity must contain these 3, all the line of, all the points of infinity, in particular these 3 of them. Does it make sense? Does it make sense? These 3 collinear line. Okay, let me draw. So I got a 3 collinear line, right? Collinear point, and then every 2 point we have a unique line. So these 3 points build you 3 different lines. Then these three different line of pencil that parallel to these 3 points. 3 lines here is 3 different pencil, right? And then this gives 3 points of infinity. And then this is a 3 different point of infinity in the line of infinity. Okay, makes sense. Okay, how about the other cases? The other cases already contain point of infinity, right? So we already have 1 point already. Where do you get the other 2 points? Points are defined as a subset of point. Huh? What? Subset of point. I didn't say must be at least 2. I didn't say that. So I just trying to give you some hint. Why this line should contain at least 2 points? Why a line should contain at least 2 points? Then this axiom is false. Then this axiom is false. Okay, I leave you think about it. I also don't know. So let's think about it. Let's continue to what we're gonna do in next lecture. So let me tell you some statements. Statement first to think about it, and then next lecture will prove it. Hopefully, we can finish all the geometry by next lecture because we need to go into commutative algebra, and then I think we will spend about 2 to 3 lectures also on commutative algebra. Only then we will start to do affine algebraic set stuff to reach Hilbert-Nonstedt, a very famous theorem in algebraic geometry. So let's tell you what the plan is. So we also can define projective plane as a tuple. Okay. Similarly, a set of a point and a set of line. Over here is a set of points and a set of line that are that satisfy 4 axioms: P1, P2, P3, and P4. So if you look at this abstraction here, the difference between affine plane and the projective plane actually not much different. Both of them are just a tuple, which is a set of points, set of line, but they satisfy different axiom, different set of axioms. Okay, one satisfies 3 axioms, the other one satisfies 4 axioms. Okay, and then what we want to say is, if we define a line in a projective plane, don't call it projective plane first, call it P2, KP2, a set of points, P2 satisfying A0 x0 plus A1 x1 plus A2 x2 equals to 0. Okay. If it is a set of points that satisfy this, does this make sense? This is a line. Does this make sense? This is a line in P2K. How about I give you some idea to think about it? So let's look at x plus 2y minus z equals 0. Okay, for example, what points you can find here? This is like a finding null space question. This is a 2-dimensional null space here. So actually there are 2 points inside this line here. So one point is 0, 1, 2, and then the other point is negative 1, 1, 0. Okay, so these 2 lines are actually different lines in projective space. But both of them satisfy this equation. Okay, so actually you really build some line. You are building some line in projective space. And the proposition is, we can show that if we take this definition of line in P2 with the point in P2 itself, and then we will see that, and then we do the point of infinity construction, and then we'll see that this is actually isomorphic, meaning there's a bijective transformation, which sends collinear points to collinear points. We will define it later, but let me quickly give you the result. This is the completion, okay, completion of R-fine plane. So once we reach this, because we proved that the completion of R-fine plane is projective, and then this projective space will satisfy the axiom we had just now. Okay? Can or not? Happy? Happy, yeah? Not happy. Got bad thing first. Next week we'll be happy a bit happier. I will prove to you next week, okay? And let's see you next week. By the way, master, please contact me or your group member.